Hello, SWIG Earth Science students, and welcome to the next recorded lecture. This week is week 11, which is soils and mass movement. So this is going to be chapter 8, which is weathering soil and mass movements. So I'm doing it in a different order, but most of the information I'm giving you is pretty much the same as what's going to be in your chapter. So your chapter starts off talking about external versus internal processes. So external processes are things that occur on the surface of the earth, and so they are going to be powered by gravity and the sun. So the things we're talking about today will all be external processes. So this is weathering, mass movement, erosion, things like that. Whereas internal processes are things that happen within the earth. So they're going to derive their energy from the earth's interior. This is things like mountain building, volcanic activity, plate tectonics. So most of what we've been talking about so far has been internal processes. This week we're going to be talking about external processes. So we're going to start off with weathering. Weathering is the breaking up of rock material into smaller parts that can then be reconfigured into new materials. So there are two main types of weathering. We have mechanical weathering, which is physically breaking down rocks. So we're basically not changing the rock, we're just making it smaller. So this can be done with wind, water, and then wedging processes, which are things that are physically getting into cracks and spreading the cracks. So frost wedging, ice wedging, same thing. Roots can do it, salt can do it, and other things can as well. The other type of weathering is chemical weathering. So this is where we're actually going to change the chemistry of the rock. We're going to break down the rock through things like dissolution. We're going to have our rocks broken into new compounds by removing or adding elements. This type of weathering needs water to infiltrate. So we actually see the two types of weathering often happening hand in hand. When we break rock into smaller pieces, we make more surfaces for water to act on. So if we look at these three piles, all have the same volume, but they have varying amounts of surface area available. So if we have just one block, that only gives us 6 sides. Whereas if we have that block broken into 8 blocks, well, now we have 48 sides. If we have that block broken into even more blocks, we'll have even more sides. So the more sides we have, even though each of those sides is smaller, gives us more surface area to work on. So we can see that it's the same volume, but we have increasing surface area. So that's how physical weathering can help with chemical weathering. Chemical weathering helps with physical weathering because when we start to break down the rocks into different components, they may be weaker and easier to break down. So if we start to break out some of those less stable elements, it will make it easier to physically break the rocks apart because we've already kind of started breaking them down. So here are some examples of physical weathering. So frost and ice wedging. This is the idea that when we have water getting into the cracks, those joints that we learned about last week, it will expand when it freezes, and so that pushes the cracks further apart. This is the exact same thing that happens every winter with potholes. Water gets into the pavement, it freezes, it pushes the cracks further apart, so more water can get into the pavement, which then freezes and pushes them further apart. Here we have an example of a bottle that had water in it and it froze. So if you ever want to freeze water in a bottle, you always want to make sure you have space for it to expand. Sheeting is a special type of weathering where we basically will form joints that are going to be parallel to the surface of the earth, and then we will have those joints or areas of weakness, and then we can have the rocks breaking off along those joints. And so this erosion is a very special type of erosion that we see when we have deep-seated plutons come to the surface. They're no longer under the pressure they were under, so they start to expand, and they basically have these materials just come off. These types of materials are very popular for rock climbers. That's what we're actually seeing in this picture over here. These are people that are climbing this half dome in Yosemite. El Capitan is another one of showing this type of joints and weathering. While it's great for rock climbers, it's also highly dangerous because we don't know when these things will break away. There's not a way to predict when they're going to fail. So yes, rock climbers like them a lot, but they're also highly dangerous. Chemical weathering is where we're actually breaking down the rocks and turning them into something else. So there are several reactions that are really important for chemical weathering. One of them is when we bring carbonic acid or create carbonic acid. So if we have carbon dioxide interacting with water, that's this first reaction, we create carbonic acid. Carbonic acid can then react with calcite, which is the primary component of limestone and therefore marble, which will then dissolve that calcite into calcium bicarbonate, a little bit of carbon dioxide and water. So basically we are degassing the limestone and then having dissolved calcium bicarbonate that's in solution. So that one's extremely important. Another one that's extremely important is we can have that same carbonic acid can dissolve potassium feldspar, which is a key component of granite. And so it will turn it into a clay mineral, which is this first one, a little bit of potassium ion as well as bicarbonate and silica. So calcium or carbonic acid rather can work on both limestone and things like granite. It's much more effective to dissolve away calcite than it is the potassium feldspar. So we see this much more intensely in limestone type of environments. We will see that if we have large amounts of limestone, we actually develop specific environments because of that. But we do also break down some of the components of granite with the same material. Weathering will always take advantage of joints. So water will penetrate joints that are pre-existing in rocks. That gives us surface area that can be dissolved upon, or it's an area where water gets in and then does some of that frost wedging. And so it will continue to expand those joints, and we will see the joints become more and more pronounced. Weathering will also always work on those sharp edges first, so we will see things get more and more rounded with time. So similar to what we saw when we were looking at our, oops, sorry, I did not mean to do that, when we were looking at our sedimentary rocks. There is differential weathering. So different rocks will weather at different rates. Some rocks will remain fairly unchanged. The crystalline rocks tend to weather much slower. Other rocks weather very easily, most sedimentary rocks. And so we can end up having situations like this where we will have a resistant rock that remains while the less resistant rock is mostly weathered away. We can see this in road cuts, for example. If you're driving along the highway, you will oftentimes see, if you look at areas where they've blasted out rock, there will be parts of the rock that is more recessed. Those are the areas that are less resistant, or I'm sorry, more resistant, yes, less resistant to weathering. So that's more susceptible to weathering, so it gets removed. Here's another example. We see two tombstones. One is from 1868 that looks completely fresh because it's granite. The other one is from 1874, so it's actually a younger tombstone, but you can't read it. You can barely read it because it was made of marble, which is metamorphosed limestone, and so it's susceptible to that carbonic acid that forms in rainwater, actually. So we can see here that while the potassium feldspar in granite is also susceptible, it's not nearly as susceptible as the calcite itself. So the story here is, if you want your tombstone to last, don't pick marble tombstone. It's not going to last. So once we weather out that material, we then will turn that material into a thing called soil. So regolith is the name for broken up rock, or also called the rock blanket. It is, the weathered material. We turn that material into soil when we add other stuff to it. So soil will have a certain component of mineral matter, a certain component of air and water, and then a little bit of organic matter. And that's what makes it soil as versus dirt. So there are different definitions for these things based on who is looking at them. So if you are a soil scientist, you say that soil is solid earth material that has been altered by physical, chemical, and organic processes such that it can support rooted plant life. If you are a structural engineer, you say soil is any solid material that can be removed without blasting. Two very different definitions. They both serve their purpose. Soil, especially from the soil scientist's definition, has horizons, which means it has different layers. Not all soils have all of the horizons. Depending on the development of the horizons is how we classify the age of the soil. The soil becomes more than dirt when it has organic materials in addition to that weathered rock material. Soils can either be residual, which means they form where they are found, or they can be transported, which means they have the materials for them have moved at a distance. So the characteristics are going to depend on the climate, how much water in particular is available, the topography, so if they're on the sides of a hill, if they're in a valley, flat slopes, things like that. What is the parent material? So what rock are you breaking up? How much time? So has the soil had time to develop? Has it had time to mature? And then what organic processes are happening? So for example, soils in desert environments have a very different profile, is what we call it, than soils in a humid forest region. So these horizons, these layers, have names based on their letter names. So the O layer is the horizon that is mostly organic materials. So this is going to be the decomposing leaf litter, etc. It tends to be dark brown or black because it's that organic matter. It will be at the top. Below that will be the A horizon. This is the horizon that is both mineral and organic materials. So we're starting to take some of that organic matter and mix it in with the mineral or rock material from below. It tends to be lighter black to brown. Oops, sorry, I just hit my microphone. This is where we start to have a process called leaching. Leaching is where we are going to remove material from the upper layers and transport them down to the lower layers with the groundwater. So this happens in the A horizon, and it will move clays and other materials lower to the lower horizons. The E horizon is composed typically of light colored materials. This is where we're really in the zone of leaching. So the A and the E horizons are the zones of leaching. The E horizon has experienced much of that leaching. So we're removing many of this material and leaving behind light colored material. And we're pulling the clays, the calcium, magnesium, iron to those lower horizons. The B horizon is where we have the zone of accumulation. So this is the area where all of that material that leached out of the higher horizons collects. So it's now going to be enriched in clay, iron, silica, carbonate, or any other material that's been leached from the overlying horizons. There are many subtypes of B horizons. Some of them have their own designations, such as there's a K horizon that is particularly enriched in calcium carbonate, and it tends to be white. So there, it depends on what is coming down from the upper layers, what the B horizon will look like. The C horizon is the lowest true horizon. It is composed of partially weathered or altered parent material. So this is the broken up regolith, basically. This is the broken up rock. And it can have some staining from upper horizons as well. And then below the C horizon will be the bedrock, which if it's given a designation as R. And so this is the unweathered, unaltered parent material. This is a summary of the same thing. So a soil profile refers to those distinct layers we see vertically as we go down from the surface. So the O and the A horizons are where we have the organic material. O is entirely plant material. A has that first combination of the mineral material mixing with the plant material. E is, along with A, the zone of leaching, so it tends to be lighter in color because we're removing much of that material to the lower B horizon. The B horizon is the zone of accumulation. Again, it's bringing in the materials that were leached from the higher horizons. There are many subtypes. Caliche is called a K horizon. That is that calcium carbonate, which can be white. And the C horizon is directly over the parent material. It's only partially altered. So this is the broken up material that works its way up into the higher horizons. and then the R is that actual parent material. Sometimes we encounter a layer called hardpan. This is where we have a compacted horizon that is impermeable. So that means water can't move through it. It can actually be cemented. So basically we hit a really hard layer that we can't get through. And it basically forms a barrier for any leaching or accumulation because the water can't get through. Color is always dangerous to use in geology. Minerals really emphasize that, but color is tempting to use because it's very obvious. So the O's and the A's, because they have those organics, tend to be very dark colored. The E horizon tends to be light because it's been leached. It's removed much of the material. The B horizon has the most variety. It can be yellow, it can be brown, dark red, white. It all depends on what that material that was leached is that now is accumulating. K is a type of B horizon, a subtype of B horizon that is white. And then C also will very much depend on the parent material. So if you have a dark parent material, it'll be dark. If you have a light parent material, it'll be light. We also classify soils based on their textures. So this is going to be the proportions of sand, silt, and clay. Sand is sand-sized. Silt is mud, and clay is the finest. If they're greater than 2 millimeters, that is where we talk about gravel, cobbles, boulders. Those are larger particles. We can estimate in the field, so we often will bite the rocks. If it is gritty on your teeth, that means it's actual sand. If it feels fairly smooth in your hand and you rub it on your teeth but still is gritty on your tooth, that means it's silt. If it's completely smooth on your tooth, then it's clay. In reality, the way we actually figure these percentages out is that we refine, we take samples and we filter them through different progressively smaller sieves in the laboratory to determine what size particles we actually have present. But we then will plot the percentages of sand versus silt versus clay on a diagram such as this, and where it falls will give us the name. So anything that's maybe 60% clay would be considered just a clay. In order to be a sand, you have to be like 90% sand. So if we notice, this field here for clay is very large. This field for sand is very small. Silt's a little bit larger than sand, but still pretty small. Somewhere between 80 and 90%. And then we can go anywhere in between. So where we have a little bit of everything, that's where we have a loam. And then depending on, do we have more sand or clay, or do we have more silt, is where it falls. We can also talk about how the grains clump together, and these are called PEDs. So we can have things like granular PEDs, we can have blocky PEDs, prismatic, or platy. They will form in different horizons, and they have different sizes. So we tend to have the larger PEDs in the lower horizons. Our soil profiles will tell us the development of our soil. So the horizons will develop as the soil ages. So if we have a weak development, that means we have a fairly young soil. So our A horizon may be directly over the C horizon. So we're not forming that zone of accumulation yet. We haven't accumulated anything. You may actually have an oxidized C horizon as well. So this indicates a very young soil. A moderately developed soil is where we do have a B horizon, but it's not fully developed yet. We start to see more diversification in a horizon. A moderately developed soil is going to be thousands of years old. It takes a long time to develop a soil. A well-developed soil is going to be quite old. This is where we do have distinct horizons. We see a developed B horizon where we have actually started to accumulate material in that zone of accumulation. So we can look at the ages of soils and actually use them to develop what we call a soil chronosequence. So we can arrange our soils from youngest to oldest based on their profile development. And this gives us a recent history of the landscape. So if we have a young soil, we know something has happened to disturb that soil. So it could be that there was a landslide, it could be that we've had a vertical movement, so from like a an earthquake or something, something tells us that if we have a young soil, something disturbed the landscape. We can also combine this with carbon 14 dating and it becomes a really powerful tool. Remember, those O and A horizons have a lot of organic material in them, so we can determine how old those actual layers are. So we can actually use this to date geologic events, and that's what these images are actually showing us. Using this technique to date the offset of this strike-slip fault. Water in soil is very important. So pore spaces are the areas around the grains. Water can fill pore spaces, but other things can as well. So air can fill pore spaces, hydrocarbons, gases, many things can fill the pore space. Permeability is the ability of water to infiltrate into a soil. The amount of water in the soil is called saturation. If it's fully saturated, that means all of the pore space is filled with water. If it's unsaturated, that means the soil can hold more water. So this graphic here is showing us an unsaturated soil because we see some air. That means that there's more space for water. Water and moisture content will impact the strength of the soil. As you can see that when we have water there between our grains, the grains are not in direct contact with each other. And that means that the soil is going to be weaker. So saturated soils are more likely to fail than unsaturated soils. When we classify soils, it's rather complicated. It depends on if you're a soil scientist or an engineer. Back to those two definitions. For hazards, we tend to use the engineering classification. It's a bit better because we only really care if the soil is going to move. For agriculture, they look at soil scientist classification. Soil scientists use what they call soil taxonomy. Engineers use an engineering classification. So this is the soil taxonomy. This is a unified soil classification system. So we have, obviously this is rather complicated. I'm sorry. This is the unified soil classification system, which actually does fall underneath the soil scientist classification as well. I will show you the soil taxonomy in a second. Yes, I believe. Am I doing this right? No, this actually I think is the engineering classification now that I'm looking at it. Sorry. This is the engineering classification. So basically it is based on the type of materials present. So do we have coarse materials? Okay. Now we're going to look at how coarse are the coarse materials and then, how distributed are they? And we work our way across. So, if we have coarse materials, then we have to decide, do we have sands? Do we have gravels? Okay. So this is the extremely coarse. This is the kind of coarse. Clean versus dirty means that clean, it's mostly that material. Dirty means that there's a bunch of fine grain stuff in there as well. And then we're going to look at, okay, what is the fine grain stuff in there, basically? If it's not coarse, if it's fine grained, well then we need to look at how fine grained is it. So is it silt, or is it clay, or is it organics? And then we can look and see what other materials are in there as well. So this is a simpler classification. Basically, it's on the size of the grains. Whereas soil taxonomy is looking at the different types of soils. They have names. They all fall into special regions. Your book goes into a lot of detail on these. I will say, I'm not going into all this detail, but your book goes into a lot of detail. And so you find different soils in different environmental regions. These are the different soils. We find these in various regions across the globe. And it's going to be based on the climates as well as what materials are present, the age of the soil, things like that. Honestly, I study earth science and I wouldn't be able to tell you an aphosol versus a oxisol to save my life. This is the only people that are really going to be able to tell you a lot about this is people that study soil scientists. And honestly, I recognize a lot of these names because I was on someone's committee who was doing this. But if you're not specifically doing this, most people would prefer to use the other classification because it's something that anyone could be able to look at a soil and say, well, I see a lot of stuff that looks like sand. So this is what the soil scientists use. It is Better for agriculture, obviously, because we can figure out what nutrients are going to be in these different soils, but it is difficult for a layperson to pick up on. We care about soils because soils are where we grow all our food. Um, they're important for daily life, honestly. One of the processes that is happening at an alarming rate is a thing called soil erosion. So this is the removal of soil by natural processes. So we can have grain by grain removal by wind and water. We can have removal of material at an unacceptable rate that is currently happening in many areas. And we have removal of material faster than it's being reproduced. Those last two are when we have a problem. So if we have excessive soil erosion, our soil quality is being reduced. We're removing the nutrient material from our soils. Water quality will also be reduced because we are now not allowing that filtration to happen in our groundwater. We can also have a problem with this when we remove stabilizing vegetation. So plant roots help keep the soil in place. If we remove that vegetation, that becomes a problem. That exact problem is what led to the Dust Bowl in the 1920s. That we basically had a desert in what had been the Great Plains of the United States for a decade because of the plowing of the grass fields. So how much soil erosion occurs is going to depend on soil properties. So what is the soil? Certain soils are just easier to remove than others. Extremely fine-grained things move easily. The land use. So most soil erosion is due to improper land use. For example, looking at the Dust Bowl, we turned prairie land into wheat farms, and wheat doesn't hold the soil nearly as well as the native grasses. Topography is important. So topography, the lay of the land can naturally protect some soils from moving. And then climate. So how much wind is there? How much water is there? What is the rainfall like? Those things all impact how fast soil is removed. So we can remove 50 to 1,000 years, or it takes 50 to 1,000 years to form about 50 millimeters, which is about 2 inches of soil. Agricultural land can remove anywhere between 0.1 and 0.05 millimeters per year of soil. So that means that in a couple decades, we can remove centuries of soils. That soil doesn't come back. It takes a long time to create a soil. So we can remove that soil very, very quickly. We measure this typically in volume, mass, or weight of the soil removed. So we're not going to typically measure it in inches. That tells you how big of a problem it is, that we can't just measure the square area. We're looking at the mass of soil that has been removed. We have also, when we're looking at soils, other issues. One of them is called subsidence. So this is where we have ground failure that is characterized by vertical deformation or sinking. So we can have entire areas sinking. New Orleans is sinking. Venice is sinking. We can have small pockets where we have sinking, such as karst. What we see in this picture here is what's called a sinkhole. And then we can have local shrink and swell. I'm going to start off with karst. So karst is a landscape where subsidence occurs due to chemical weathering of the subsurface materials. It's most common in limestone and dolostone. Also, it can be found in rock salt and gypsum. All of these things are removed by water moving through the material. So rock salt and gypsum will dissolve with regular water. Limestone and dolostone need that acid rain, that carbonic acid. So we can remove 10 centimeters of material in a century. Marble is metamorphosed limestone. So when we see these damaged headstones, it's because the carbonic acid works on marble as well. We can actually use these headstones to figure out the rates, because headstones typically have the date they were erected. They have the death date. If we can estimate how thick the carving would have been, we can estimate how much carving has been removed since that time. It's pretty cool. This picture is showing us a karst landscape. So these round depressions are all sinkholes. So that's area where material has been removed. So what is karst? Karst is this landscape that we develop by removing material in the subsurface. So a karst plain is the overall region where we have karst elements showing up. Sinkholes are round depressions that form due to removal of material. Disappearing streams are streams that go underneath ground into underground caverns. A solution valley is where we have the water that is running along that karst plain will start dissolving away the limestone beneath it, and so make a steeper V-shaped valley that the water will continue to run in. Subterranean caverns are areas where we have dissolved away the material when it was below the water table, and now the water table has dropped, so that dissolved away area is open to air, and so it's open as a cavern. And then tower karst is the only one not on here. Tower karst is basically what's left behind when everything else in this plain is gone. So you'll have a isolated area of limestone that remains as a tower. That happens in typically very humid environments. I have some pictures of that to show later on. So sinkholes. Sinkholes can form from two different ways. We can either have solution sinkholes, which is dissolution from the top of the surface. So basically we are removing material by water percolating down into this depression. They tend to have more gradual slopes and they will form slowly. The other way, which is the dangerous way that sinkholes form, is called a collapse sinkhole. So this happens when there is a cavern or a cavity that's being dissolved away beneath the surface, and so this material will be dissolved on all sides, including the top. Eventually, this roofing material will get thin enough that the overburden overpowers it and will collapse down. And so these tend to have straighter sides. They happen very quickly and they're much more dangerous. These are the ones you see on the news. There's a third type of sinkhole. The third type of sinkhole is not a natural sinkhole. They are sinkholes that form in urban areas due typically to massive amounts of water moving underneath pavement. So oftentimes from things like water main breaks. And I'm going to show you some news footage of local Philadelphia sinkholes because, again, I stole this material from one of my classes back in Philadelphia. So these are local sinkholes that are not related to karst, but it's the same idea that we're removing material at depth. So, I believe.
Developing now, a big cleanup needed in one South Philadelphia neighborhood today after a water main break causes a sinkhole there. Eyewitness News reporter Dan Coote is live in Queen Village for us this morning to show us the damage left behind. Hi, Dan.
Jan, good morning to you. We're starting to see some of the neighbors, some people in the neighborhood come out, walk their pets, walk around and start poking around saying, what is going on over there? So we'll show you. This is a big water main break where, as you can see, the street has caved in on itself. Philadelphia Water telling us about 200 residents were without service, at least in part, overnight. We'll show you some video about what it was like when crews were actually here as they were quickly trying to shore up a ruptured line, doing so in the rain that has been a constant in this area for hours. Philly Water also telling us about a 12-inch main is what gave way before the street did.
Our crews responded to get the main shut down and obviously cordon off the area around the cave-in the street. At a certain point, we had approximately 200 customers without water service.
Now, they also tell us at this point this morning, those without service have had it restored. So everyone should be waking up this morning to at least water working in their homes. But as you can see behind me, Jan, a lot of work to be done by crews who will surely be returning here later this morning. We're live on 2nd and Fitzwater. Dan Coote, CBS 3 Eyewitness News.
A lot to be done there. Okay, Dan, thanks so much. Appreciate it.
So this is, I believe that same sinkhole, just different videos of it.
A sinkhole continues to rattle nerves in Queen Village. Here we go to 2nd and Fitzwater. A ruptured water main is to blame for that crater right there. Philadelphia Water Department officials tell us a 12-inch line burst. We spoke to those living in that area about this inconvenience.
My dad works in water engineering, so I asked him why these kinds of things happen, so he was able to explain to me like what usually goes on. So sometimes he said it's a leaky main or the sewer would have been failing, which makes sense. They just repaved the road, I think, on Wednesday.
Yeah, they just repaved it, so this road's been shut down like all week. So it's already been an inconvenience, and now seems like it's going to be much longer.
Well, the Philadelphia Water Department says at one point more than 200 customers were without water, but for now, water is only shut off to those in a small area between Fitzwater and Bainbridge Streets.
All right. So again, that was the same one. This is a older video from, I believe, 2018 that shows sinkholes that occurred in, I believe this is Chester County, but that were associated with the Mariner East pipeline project.
One local family is out of their home tonight in Chester County. 3 sinkholes popped up on one street, and neighbors say a pipeline being drilled right through their neighborhood is to blame. Sunoco's Mariner East 2 is supposed to run across Pennsylvania through Chester and Delaware counties. NBC 10's Brandon Hudson talked to a homeowner who's worried about what happens next.
The sinkholes in TJ Allen's backyard are covered, but the fear remains.
Well, I'd like to know if my house is safe.
Allen says a sinkhole formed over the weekend in his yard and a neighbor's yard too, forcing that family from their home. He believes they're directly linked to the construction of Sunoco's Mariner East 2 pipeline in Chester County. A Facebook Live video shows crews from the State Department of Environmental Protection and Sunoco working to cover them up.
There was 11 cement trucks that dumped 11 loads of cement in my yard.
We first met Allen in November when he claimed pipeline construction caused this sinkhole to form on his West Whiteland property. He says these new problems started soon after the state granted Sunoco permission to start construction again.
What's the point of the DEP if they can't shut Sunoco down?
Allen says when that second sinkhole opened, it was deep enough that it could easily fit this car and truck inside. He also said the work is causing problems in his driveway. These cracks are now wide enough to fit a pin inside. Have you started looking anywhere else to where you want to live, or?
No comment.
This is atrocious situation for the constituents of my district. This is potentially a dangerous situation.
We talked to Pennsylvania State Senator Andy Dinniman today. He wants the state to halt drilling again.
This pipeline goes adjacent to schools. It goes adjacent to retirement communities and nursing homes.
We made numerous phone calls and emails to Sunoco, but they did not respond by our deadline. In West Whiteland, Brandon Hudson, NBC 10 News.
So this is not a sinkholes forming in urban areas is not just a Philly thing. We see this in St. Louis. You see this in any major city, especially cities that have older infrastructure where you can have things like those pipelines bursting or your sewers maybe leaking. Anywhere you can remove materials at depth. If you remove materials beneath a street, well, if there's no longer any dirt to support it, it's going to collapse. Another place that we see native karst is in cave systems. So cave systems are where you've had dissolution of material below the water table. If that water table then drops, those caverns become exposed to air. So then we have these magnificent features. So we can have additional deposition of material once that cave is open to air. Because remember when I showed you the chemical reaction of carbonic acid interacting with calcite? Well, that leaves calcium bicarbonate in solution. If that water then continues on, it can deposit that calcium bicarbonate, and then we can go in the opposite direction. So you can actually form calcite formations, and this is travertine, which is then cave deposits. So if it's hanging from the ceiling, it's called a stalactite. So basically you have water dripping down. As it hits the tip, it deposits a little tiny bit of calcite and then drops down. It then hits what will be called a stalagmite on the floor, and again deposits a little tiny drop of calcite where it hits. And those two will grow towards each other. If they connect up, that's called a column. We have these tiny little ones are called soda straws. the tiny itty bitty ones, they tend to be just hanging from the roof. Again, this is made out of a thing called travertine. If you ever go to a cave as a tourist, they will ask you not to touch the formations because the oil from your hands can actually interfere with that process of depositing new calcite. So that's why they ask you not to touch these formations with your hands. And so here are those pictures of the tower karst. So this is what's left behind when everything else is gone. It's very common in humid tropical regions. We don't really see this in the US. Disappearing streams and springs. So when a stream suddenly goes beneath the ground, when it goes into one of those underground caverns, that's called a disappearing stream. This happens because karst is so permeable, it's so easy for the water to infiltrate it. You can also have the sudden appearance of water, and that's what a spring is. So always beware of, quote, spring water that comes from a karst area. That water is coming up through a spring, that is true, but it hasn't been underground for very long, so there's not a chance for it to really purify by traveling through the rock. You can also get karst in frozen landscapes. So permafrost is frozen soil and sediment. If it is to be permafrost, it has to remain frozen for at least 2 years. The melting of permafrost causes compaction and subsidence, and so we call this thermokarst. We can also have large-scale subsidence due to soil compaction. So if we rapidly deposit fine sediment, water fills the pore space typically. If we remove that water, we will have compaction because we basically are removing what's keeping the grains apart and it squishes down. So this happens a lot in deltas. We can also have deposition of sediment that's cemented with soluble materials. If we remove that cement, we will then have compaction because we're removing the material from the pore space. We can have what's called a collapsible soil. So loess, which is a wind deposit that's loosely bound by clay and water-soluble minerals, it will dry out very quickly. If water ponds on its surface and then starts to percolate through, it dissolves the cement and then the entire deposit collapses. What we're seeing here repeatedly is that if we remove something in the pore space, it collapses. We can also have organic rich soils. If we drain water from those organics, they'll dry out and compact, which, we have this happening with decomposition. If we drain wetlands, we see this happening. So basically, anytime you remove something from the pore space, that pore space then will crunch down and you can't reinflate these soils. So this leads to large-scale compaction and subsidence. We can also have subsidence from other hazards. So earthquakes obviously can cause the land to drop down. If we empty a magma chamber, that then has a void in the ground and we can have subsidence into that magma chamber. We can have other magma structures like lava tubes also collapse. A more localized issue are what are called expansive soils. So these are soils that will change volume in response to water content. So they will shrink during dry periods and swell during wet periods. So basically, when water comes in contact with these soils, they suck them up like a sponge and they get bigger. And so they swell. So these happen with a particular type of clay called smectite. You can observe this by looking at drying cracks. So basically we see these mud cracks. We can see cracks in the pavement due to this expansion and swelling, which basically makes the ground go up and down slightly. Wavy pavement, that's what we're seeing in this one. Again, that's due to the ground going up and down. That's what we're seeing here. And tilting of signposts. So that means if all of your signposts are tilted in your neighborhood, that's probably not a good idea or a good sign. This leads to damage to building foundations and other infrastructure. You can imagine if the ground's just subtly going up and down constantly, that's not a good thing. We can also have the same thing happen due to plants. So plants that suck in water will cause the ground to shrink. They can also swell up when the roots get bigger, so plants can cause this issue as well. So anything that can make that ground go up and down vertically is a problem. We can also have issues with freeze and thaw in soils. So frost susceptible soils that have enough water content in them will actually change vertically as the water freezes. When water freezes, it expands by about 9%, and we call this frost heaving. That's what we see in this picture. When we then move the soil up, that gives us space that additional water can percolate down so that it will freezes and we get an additional expansion. So for this to happen, we have to have temperatures below freezing in the soil long enough for that ice to actually form. So it's warmer typically in the soil, so that means we have to have very cold temperatures for an extended amount of time. We also have to have water in the soil to form a large enough amount of ice to lead to the heave. And we have to have the right sediment to allow that water to draw down through the soil. So silts have this happening a lot. In the US, the regions at risk of these things are going to be dependent on the subsurface geology. So wherever we have limestone and Yellowstone, oh wait, look, where we're at has a lot of that. No wonder we have all kinds of, sinkholes around here. If your subsurface is susceptible to dissolution, we can have issues. Climate, frost heaving, that's going to be happening more in the northern climates. Sediment supply, if we have areas where we could have those compacting soils, and areas that are prone to earthquakes and volcanoes can also have those localized hazards as well. Subsidence and soil movement can be problematic. Sinkholes are the first thing that most people think about when it comes to subsidence hazards, and yes, they can be problematic. That's what this first picture is showing us. Karst environments, in addition to having those potential for large sinkholes, they also have the problem that pollutants enter the groundwater much easier. The residence time in karst environments is also very short, so you don't have a lot of time to clear away these impurities. Another issue with subsidence is permafrost melting. This is happening on a much faster and larger scale with climate change. So much of the infrastructure in areas that have permafrost is dependent on that permafrost remaining frozen. Now that it's not, those buildings aren't designed to be on non-frozen soils. And it's a very expensive retrofitting to make them stable. We're also seeing subsidence of deltas, which leads to flooding and loss of wetlands, which leads to many other issues. So these are almost quiet hazards. They are slow hazards, but they are still very problematic. We can also have local damage due to volume change. Here's an example of a house. We see the ground surface in 1956 versus the ground surface today, which would be sometime in the 2010s. So this is 60 years of difference, and it's 10 to 16 inches of subsidence. That's an issue. This is not going to make your house very stable. I'm surprised there aren't more cracks in these brick walls. So we see a lot of local damage from volume change, from either expansive soils or that frost susceptible soils. But it's similar damage. We see tilted poles, we see cracks in foundations, we see tilted steps, sidewalks will buckle, we can have potholes, wavy pavement. We're going to see very similar problems. If you have a brick house and you see damage like this at the corners, that's not a good thing. We have other links to other hazards as well. This is another lecture I stole from much of my hazards course. So flooding, if your land has subsided below sea level, guess what? You're now below flood level. We saw this in New Orleans. Well, we see this quite often in New Orleans, rather. We can have mass wasting, which we're going to talk about later on in this lecture, so I won't go into that very much. Climate change is going to cause our water table to lower, so this will lead to subsidence because we're removing material from that pore space. This can lead to desiccation cracks, which are mud cracks, or full-on earth fissures, which is what we see here. We're also going to see climate change will increase our permafrost melting, so this is going to get worse and worse. Good of subsidence and soil processes. It produces our PEDs that increase soil production, so we're going to make our soil faster even though we're also eroding it faster. We get scientific data. As far as for karst and caves, they're cool, so there's some tourism and aesthetic value there. We are developing ecosystems and habitats as well, and water resources. So while karst springs aren't very good at filtering, they are very productive. So we get a lot of water out of them. Humans and subsidence. We make this bad. We make this very bad. We make this really bad. Can I say that again? We make subsidence much worse. So we like to pull stuff out of the ground. So groundwater, We are pumping groundwater at alarming rates and hydrocarbons. When we pull this stuff out of the ground, the same as when it happens naturally, if we pull it out of the pore space, those pore space will then compact and we can't get that back. So that's what we're seeing here. That when we pull this water out of the pore space, that pore space then contracts because there's nothing holding those grains apart, so we will see subsidence. We also see the water table going down, which is a problem. Here we see, I love this image. This is a post that is showing us the ground level from 1925, 1955, and 1977. And I'm sure it's gone probably the same amount to now. So this is a person standing here. This is how much subsidence we're seeing in, what is that, 50 years. That is insane how much subsidence they're seeing, in this, area of California, mostly due to groundwater withdrawal. Oh, guess what? California has issues with water. I wonder why. Humans increase subsidence with wells that we're pulling out water. With mining, we're putting big holes in the ground that can collapse. We're melting permafrost due to our actions. We alter rivers, so this will alter our delta deposition. We alter our surface drainage, which will then alter our water infiltration. So we're basically funneling water to only certain areas, which will make it erode there faster. And we can have locally poor landscaping, so trees next to buildings can cause shrink swell. So humans really do impact this a lot. For mitigation, so we basically have to stop the harmful actions. So reducing fluid withdrawal, trying to put stuff back in to the ground is not really helpful because you can't undo that compaction, and actually injecting things into the ground causes other hazards like earthquakes. Trying to regulate our withdrawals, our mining, engineering to make sure that we're prepared for that permafrost to not be permanently frozen is important as well. In less developed areas, trying to restore more natural deltas and wetlands is key. That's not going to happen for places like the Mississippi. Managing our drainage is very important to make sure we don't have the shrink swell. Expansive soils are locally a major problem. One of the ultimate ways to deal with that is to just remove the soil. So there are other ways you can try to handle it by dealing with proper drainage, putting barriers in place, using your land more intelligently, or just removing that material. Adjusting to subsidence, very little attention is given to this other than sinkholes or Venice's sinking. It's on a personal level, it's important that areas prone to subsidence are used intelligently. We can figure this out by geologic and soil mapping to find the areas of those potential hazards. We can also look at surface features to indicate hidden dangers. Do we see those mud cracks? Do we see the wavy pavement? Things like that. Subsurface surveys allow us to look under the ground, and so we can actually see cavities, knowing what hazards are present in disclosures, and then ultimately we can reuse hazard lands. So Springfield, Missouri, I know does this, where the parks are all areas where sinkholes had opened up. There are significant sinkholes in the city because the paved areas mean that water is funneled to the areas that can infiltrate, so water is being focused in those areas, which makes them dissolve faster, and so sinkholes have the potential to open up. So when a sinkhole opens up, the city buys up the land and then turns into a park so that there's more green space, but then also they know that's an area where a sinkhole has opened, so it's possible that more will open there as well. Okay. Now we are going to move on to mass wasting. So I'm going to show you a video that I'm going to accelerate. This is happened after the massive rains in 2021 from the atmospheric rivers that hit California. In 2023, the same thing happened actually. So I'm going to speed this up to 1.5 because honestly, we don't need to have it go slow speed. So this is mass wasting. So this is mass movement of materials downhill. So this was a highway. It no longer is a highway. Now it is a gulf, basically. We can see water and other materials falling down this hill. So this happened when, there you just saw materials falling. This happened due to saturation of these soils, that the soils lost strength, and we had mass movement of material up the hill. It hit this road, removed material from the road, and then once material started moving, it just moves much easier. But we can see some downed trees. It should spin around in a second and look up as well. Here we go. So we see all these downed trees as from material that came from further upslope. So we are going to see this material that came from further upslope and came down the slope and then hit the road and then took out the road. So this is what we're going to be talking about today. All right, I think that's enough of that. Oops. All right, so mass wasting is a comprehensive term for any type of downslope movement of earth materials. So landslides, earth flows, debris flows, rock falls, avalanches, all these are mass wasting or mass movements. Landslide is actually technically a general term as well. Slopes are the most common landform on Earth. There are several segments to them, so the gradient or the angle of the slope will determine its nature. Steep slopes tend to have a free face or a cliff face, and at the bottom they will have a talus slope where rubble accumulates. Gentle slopes will have a convex slope, so they curve up at the top. Then there will be a straight slope in the middle, and then we'll have a concave, so it curves down at the bottom. The angle of the slopes will also determine how movements happen. So different gradients lead to different types of slides. So steep gradients are more prone to falls. Gentle gradients are more likely to slide and slump. I will discuss those words in a moment. You can have both in one slope though. So for example, you might have more falls on the upper portion where it's steeper, and you might slide more towards the bottom. So like for example, on this image, within this cliff face, we're going to have falling, but within the talus slope, the debris slope at the bottom, we will have sliding in there. So the classification of downslope movement is going to be based on the mechanism. So how is the material moving, the type of material it's moving, how much water is present, and then how fast is it moving. Mass wasting classifications are not cut and dried. People use different terms for the same thing. They may refer to different things by the same term, so it is a very loosey-goosey type of classification. Falling is where we have a free fall of material, so rock fall, it's pretty much rocks falling. Sliding is where we have downslope movement of a coherent block along a planar slip plane. So we have coherent blocks of movement falling or sliding along a flat surface. Slumping is where we have those coherent blocks along a curved surface. So this is where we create slump blocks. So the difference between a slide, here we have a slide versus a slump. So that curved surface is what makes it slumping, is versus sliding. Flowing is where we have unconsolidated material moving downslope. So sliding and slumping is coherent blocks, flows are incoherent blocks. And then creep is when it's extremely slow flow. So it's moving very, very slowly. Another classification scheme, which is looking at falling, sliding, flowing. You can also have, the most common one are these complex slides where you have multiple things happening at the same time. One of the few that is very defined is an avalanche. An avalanche has to have snow and ice in it to be an avalanche. The earth flows, the flows tend to have more wet materials in them. The slides tend to have more dry materials in them, but there's a lot of variation in the names of these terms. So creep is always going to be the slowest one. This is what creep can look like. So we can actually see that these trees are bent because this slope that they're growing out of is very slowly, very, very slowly moving downhill. And so the tree is actually bending to make sure it keeps going straight, even though its roots, the surface is moving with down the hill, its roots are stuck further up the hill, so it's actually going to bend to keep making sure it goes up straight. So here we have an example of a complex slide. So we have flows in the lower portions, we have slumps in the upper portions, and it can change depending on the angles of the slopes as well as what materials it's encountering. So why do we have failure on slopes? So failures on slopes are going to occur when the driving forces, which is the thing that's trying to move the material down, exceeds the resisting forces. So the thing that's moving the material down is its weight, particularly the weight that is parallel to the slope. Resisting forces are the forces that are trying to keep the materials in place. So this is going to be the shear strength. This is proportional to the normal force or the component of the weight acting perpendicular to the slope. So when the driving forces are greater than the resisting forces, we get failure. The angle of the slope will impact the ratio between driving and resisting. So the greater the angle, the greater the driving force. So this thing here is basically showing us how the weight is distributed between driving forces and resisting forces or normal forces. So the weight can be, which is this straight down arrow, can be broken down into a component that is perpendicular to the slope and parallel to the slope. The one parallel to the slope is going to be the driving force. The one perpendicular to the slope will be the resisting force. That's the force that's holding it steady. So as we increase our slope's steepness, we are going to end up driving that normal closer, that we will have more of it will be in that driving force and less of it will be in that resisting force. If we have a shallower slope, more of it will be towards, I'm not very good at drawing, am I? More of it will be towards the normal, holding it in place, and less of it will be towards the driving. So the steeper the slope, the greater the driving force. You can think of this as like a pendulum, that if we tilt this entire thing in that direction, we're going to swing our normal towards the driving, so we're going to have more of a driving component. If we take it in this direction, we will swing it more towards the resisting. So what determines these forces? It's going to be dependent on the types of materials, the angle of the slope, which I just explained, the topography, the climate, vegetation, water, and time. I will go through each of these. So the earth material types. So this is, what are the materials? Certain materials are just weaker than others. They're more prone to sliding. Part of it depends on whether or not they're cemented. So are they cohesive? Are there planes of pre-existing weakness? If we have an area of pre-existing weakness, that means that we are likely to fail. How easy does water move through? Does water get trapped? If water gets trapped, that means we're lubricating the beds and they're much easier to slide. Another thing that happens are these things called daylighting beds. So when our bedding planes are essentially parallel to the slope, that means that we basically have made a plane of weakness that is parallel to our slope. And so they're very likely to fail. They're called daylighting beds because as we erode away, we see little sections of the progressively deeper beds because, again, the bedding plane is parallel to the slope. So what controls the shape of the slope? Shape of the slip. When we have a curved surface, we get rotational slips. So that's where we get those slumps. If we have a translational movement, that's where we get the planar flat slips. So that is somewhat dependent on what our earth materials are as well. Slope and topography. This is going to determine our potential energy. So the steeper the slope, the greater the driving forces. The higher the topography, the greater the potential energy. So rock falls tend to be associated with steep, high slopes. Soil slips on steep slopes typically will become more flows on the lesser slopes. Shallow slopes are more prone to things like creep. So the more violent things tend to happen on the steeper slopes. Climate is important because climate is going to determine the typical weather patterns in a region, particularly the amount of water available, also the amount of snow and ice, and what vegetation is available. And we will see how both vegetation and water are very important for slopes in a second. Vegetation is very important because vegetation can, note I'm saying can, stabilize slopes. It also can provide a cushion against the rain, which gives greater time for infiltration so that it kind of spreads it out so it's not just all hitting at once. The roots can, again I'm saying can, strengthen the slope. The downside is that plants will add weight. So it increases both the resisting because it's holding it in place and the driving force because it's adding weight. Whether or not it is more towards the driving or the resisting side is going to depend on the angle of the slope and if the proper vegetation has been planted. So if the wrong vegetation is planted, you've just added weight and you haven't added any stabilizing, so you can have something like that happen. Water is extremely important because water will lubricate the slopes. It adds saturation, which allows for immediate slip. It also allows for future slip if you have deep infiltration, that you then are basically floating the grains against each other so they're not held together as closely. Water can also erode away the base of previous slopes. Removing the toe, the front of old slides, actually allows slip to resume. So you can actually remove the thing that's holding back the slopes. We can also have liquefaction of expansive clay, so basically you're creating a slip plane. So you tend to have massive amounts of mass wasting after large rain events. Time is important because forces will change in time. So we can have seasonal changes, so changes in like the water content, for example, and vegetation. Weathering will reduce the strength of the rock layers. We're breaking them down, which will make them easier to fail. We can also have a positive feedback. So as the slopes lose stability, they become more and more unstable. Avalanches are particular mass wasting events where we have rapid movement of snow and ice. Other stuff can be caught up in them, but it's necessary to have that snow and ice. This will occur when the snow is steeper than what's called the angle of repose. So the angle of repose is the angle where the slope is stable. Loose snow avalanches will start at a point and then widen out. Slab avalanches start as blocks. You can have both in the same avalanche. They tend to follow what are called chutes or the tracks of previous avalanches. So this picture is showing us two of those tracks. Here we have maps of past chutes. So these are the areas where we have the greatest potential for hazard. Oftentimes in avalanche-prone areas, they will set off avalanches when the snow conditions are appropriate, that they're a hazard, so that people don't set them off themselves, because most people caught up in avalanches cause the avalanche themselves. So this first video is from Telluride.
Oh, there it goes! Woo!
There, it's starting up here.
Oh,
it's coming down.
What? Woo! Woohoo! That's insane.
So obviously when they do this, they evacuate the area. I think my dogs are hearing it from my headset, so sorry about that.
Whoa.
So this one would have been a loose snow avalanche. It started from a point and came down. So now I'm going to show you one that is scientifically. They set up an avalanche for scientific purposes.
It's 6:30 in the morning, minus 10 degrees Celsius. A convoy of avalanche researchers and journalists heads out from the winter sport village of Anzer in Valais. Around 1 meter of fresh snow has fallen in the last few days. At 1,700 meters, the group reaches a lookout point where they can have a clear view on the avalanche dynamics test site, where the simulation is going to take place. Francois Dufour, of the Institute for Snow and Avalanche Research, SLF, is in charge. Checkpoints report to him via radio whether tourists are in the danger zone. An experiment on this scale hasn't taken place since 2012.
What we are investigating here are very large avalanches. That's what we are interested in. We are not interested in avalanches falling a mere 200 meters. We are looking into the ones that go for miles. We also need to have nice weather so that we can clearly film what's going on. It's not easy having all these conditions in place.
Before the blast is set off, a helicopter, equipped with a laser, records the snowpack to measure how much snow will be swept away with the avalanche. As the moment of the blast approaches, tensions rise.
5 minutes to the blast.
And then at 10:30, 15 kilos of dynamite explodes on the crater Bess at an altitude of 2,700 meters, causing a snowslide.
Das ist los, eine Lawine kommt.
That's it. A beautiful avalanche is coming down.
As snow thunders down to the valley, it gathers momentum, reaching speeds of up to 250 kilometers per hour, while cameras and probes on the test site measure every detail of its descent. The experiment has been successful. Now the team can celebrate.
We are all satisfied and happy as we were able to measure everything we set out to measure. These results are very important for the future of avalanche dynamics studies.
Wir warten seit Jahren.
We have been waiting for years to be able to trigger such an avalanche. For us, it's a pleasure to see it and to know that this avalanche didn't cause any accidents.
The experiment has provided important data that will improve avalanche modeling and ultimately contribute to the protection of the public.
So again, often avalanches are purposely triggered just so that they can't be accidentally triggered by people out. Avalanches are one of those that if you are out in an area that there are signs posted, typically they use black warning signs. Do not go in those areas because that means the snow is unstable and you can easily trigger an avalanche, endangering yourself and other people in the area. So areas at risk are areas of high topography that have steep slopes, so mountainous areas. Factors that increase the potential of slides are going to be urbanization. That is removing some of the stabilizing forces, is also increasing runoff. Tree cutting expands slide-prone areas as well. When I used to drive from Philly back to St. Louis, or drive kind of along here, and I just went way south, but whatever, I would go through these areas, and there was one spot along the Pennsylvania Turnpike that they had completely clear-cut these hill slopes, and I know at some point those hills are going to collapse because they've removed all the stabilizing vegetation. Changing in climate will increase regional precipitation, and that can lead to additional slide hazards as well. So in the US, we have about 25 deaths per year due to landslides. If we include evacuation collapses, that increases. We have billions of dollars of damage, damages to homes, roads, and railways. There are linkages to other hazards, so slides can result from other hazards like earthquakes and volcanoes and storms and fires. Slides can also cause flooding if they dam up materials. They cause damming. They can cause tsunamis if they go into the water. So slides are often linked with other hazards as well. Landslides can remix geologic materials. They can create new habitats. We can expose mineral deposits, and we are basically moving materials down slopes, so we're advancing that development of new materials. Humans and slides. Landslides are natural. Humans make them worse. So we tend to destabilize slopes. So we often will remove the stabilizing forces. We will also increase the weight on slopes. We alter runoff patterns. We have excavations where we are, cutting into the supporting material. We remove vegetation. We change the grading of land surfaces so we can actually make slopes steeper. and thereby altering the slope gradient. So what we see here is that building a couple of these houses, we decide, oh, we want to be up, have the nice view. So we're going to cut a nice little flat area. Oh wait, our flat area is not big enough. Let's fill it in a little bit. So we're adding weight. We've reduced the support, we've removed the support rather for this upper material. We've added weight. We did the same thing down here. This is just a, disaster waiting to happen. To mitigate slide hazards, we need to identify potential slides. So we do this by looking at the slope stability and creating maps of that slope stability, which then feed into landslide hazard maps. And then we can then create risk maps. So this will tell us what areas are at risk for landslides. And then the important thing is best practices in areas that are prone to slides. We can try to control drainage so that we don't have lubrication of those potential slides. So we do this with drains and trying to reduce infiltration and trying to shore up areas. So some of the things that we can do is we can change the slope. So we can try to make sure that we use grading. So we reduce the gradient. We can do benching or terracing so that instead of one long slope, we now have several smaller segments with these like flat areas in between that can stop the landslide from being the entire slope. We can add support. So gabions are these wire baskets full of rock. You've probably seen them along the roadside. We can put walls. It's important to have proper drainage so you're not having water collect behind your wall. So if you're having something solid, you need to make sure you have drain holes. The gabions have their baskets of rock, so there's easy drainage in there. That drainage is extremely important. We can also have warning systems. So for example, a slide starts high up in the mountains, warnings go off. We can have sirens, or we can stop trains that are moving through that area so that they're not going to be impacted. What can we do? Ask yourself, is the view worth it? Is it worth it to be on top of that hill if that hill's going to collapse beneath you? We need to assess the potential for slides before purchasing land and using land inappropriately. Trying to ensure critical facilities are not in the path of potential slides, especially in mountainous areas. It's important to treat the cause of the slide, not the symptoms, so trying to make sure that we don't have those issues with the infiltration. Avalanches tend to be triggered by victims, so following those warnings, educating the public, and then we can also try to repurpose land. So that's what we're seeing in this panel, is repurposing this land such that we won't have a future slide as well. This next video is from the USGS, talking about their landslides. It is rather fascinating. It shows you some nice videos. I will note that their terminology is different than what I've been using. So like I was saying, there's not cut and dried terminology. Everyone kind of uses their own words. So here is the USGS.
Almost every citizen in the United States could potentially experience a landslide. Landslides come in quite a few different flavors, and even with our small group of 20 here at the USGS, we have some of the world experts in each of the different kinds of landslides. They're very slow-moving, deep-seated landslides, which don't threaten lives too often, but they can do a huge amount of damage to property. If you imagine your house slowly moving down a hill, we have very fast-moving landslides which are a danger to human beings. These are called debris flows. These move at 30 miles an hour, and if you imagine sort of a consistency of concrete with huge boulders in it rushing at you at 30 miles an hour, you're not going to get out of the way. So these kill a few people around the world every year. And finally, there are rock falls, which probably are the kind of landslide that most people are familiar with, when huge boulders fall off of a cliff along the side of a highway and smash a car.
Within the Landslide Hazards Program, we have 3 specific tasks. One is developing tools and methodologies that can be used to characterize landslide hazards. The second is to respond to landslide disasters, to provide expertise and assessments. And then the third is outreach, to try to educate the public about landslides and landslide hazards as best we can.
The landslide program is looking at an application called Did You See It?, in which members of the public can come to our website and give descriptions of the landslide, the characteristics of it. They hopefully will even be able to post photographs of it, and we'll start to build a database that will be very useful to us scientifically.
Hundreds of thousands of landslides occur in the United States every year, of every imaginable scale. We would like to ultimately, someday, have an inventory of all those landslides.
In the area of landslides, we've been working with partners in the National Oceanic and Atmospheric Administration's National Weather Service on a debris flow early warning system.
I'm really proud of how this joint collaboration between NOAA and the USGS has resulted on a warning system that is helping the people in the communities that are susceptible to the debris flows, at least in Southern California, to be safer and to be more resilient.
Within this warning system, the Weather Service takes the role of issuing the forecasts and measuring what sort of rainfall is occurring, and then they have the system for disseminating watches and warnings. The USGS brings to the table our knowledge about what sort of rainfall conditions will lead to the landslides and what areas would be the most susceptible.
The debris flow warning system involves for the National Weather Service to use models developed by the Geological Survey, and in combination with our own observations or using high-resolution radar and weather forecast, to tell the community and the emergency managers what are the areas that are at an imminent risk of having a debris flow, which is mudslide or mud flows as they are commonly known.
Yeah, a number of USGS scientists produced a book in association with the American Planning Association just a few years ago. This takes you step by step through some very simple procedures that you can do to make your family safer and your community safer. This is a truly a national problem. It's a problem that's affecting our economy. It's causing billions of dollars in damage every year. And like many other natural hazards, they actually do endanger people's lives occasionally, and we need to sit up and pay attention.
The Landslide Program has a website where we provide information about our research or our ongoing projects, and that is landslides.usgs.gov.
So I always think it's nice to see the actual pictures, because that really is going to help the most to understand these things. So now I'm going to show you the pre-lab video for week 11, which is going to be aerial photographs and satellite images. So this one's about 10 minutes long.
Hello, welcome back for another pre-lab video. This week in lab, you're going to be taking a look at some two-dimensional pieces of paper that depict the surface of Earth. Some of these will be photographs that have been taken from airplanes. Some of them will be photographs that are taken by satellites orbiting the planet. And others will be depictions of the Earth called topographic maps that show the shape of the land. Where am I? Here I am, I'm out in the woods. I need to get back to the lab in time to run the class, and I don't really know which way to go. If only I had a map, or maybe a GPS, something that could tell me exactly where I am on the landscape. I would love to be able to find my way out of here. If only I was like a bird and I could fly up above the landscape and look down and see where I am relative to the landscape. That would really help me figure out which way to go. On the other hand, maybe there are some places I'd like to look at from above, where it's dangerous for me to actually be on the ground in that spot. I'm thinking about maybe like a volcanic eruption or something like that. It'd be safer to look at that from the perspective of a picture rather than actually being on the ground up close and personal. So that's what this week's lab is about, taking a look at two-dimensional paper representations of the world we live in. The first set of media that you'll be looking at in this week's lab are these stereograms. You use a special set of glasses called a stereoscope to view a stereogram. Basically, it's a double photograph that are taken from slightly different positions. And if you go ahead and look down through the stereoscope with it adjusted to be as wide as your eyes are from one another, you basically will get this sort of false three-dimensional sense of the landscape. So it's kind of neat. It becomes sort of a virtual 3D image. All you have to do is set down the stereoscope on top of the stereogram and put your eyes over it. And some people actually can view stereograms without the benefit of the stereoscope just by crossing their eyes in a very specific way. Another set of images that you'll be looking at are simply photographs that are taken by satellites that are orbiting Earth. These show us what the Earth looks like from above, and you'll see things such as volcanic eruptions and oil spills. You'll be able to compare the same area under two different time periods, so basically like when it's very rainy versus when there's a drought, or similar sorts of before and after kinds of comparisons. The final set of images that you'll be looking at are probably the most complicated. They're called topographic maps. And topographic maps come in different scales. For instance, the one up here in the upper left is a 1 to 250,000 scale map, which means that 1 inch on the map represents 250,000 inches in real life. Or 1 centimeter on the map is 250,000 centimeters in real life. The one in the middle is a different scale, 1 to 62,500. So basically that one's more zoomed in. And the one down in the lower right is probably our most common topographic map scale, 1 to 24,000. Whatever the map is that you're looking at, it'll have a scale bar at the bottom that will tell you what the ratio is of the map to real life, and then it'll also show you visually how far a mile is, or a kilometer, or some number of feet on that map. Some of the maps you'll be looking at utilize the public land survey system method of basically divvying the land up into a series of smaller pieces that can be specified. So, for instance, if we want to examine this congressional township right here, we can describe its position on the surface of the Earth relative to two lines, a baseline which trends east-west, and that's this line right here, and a principal meridian which trends north-south. That's that line right there. So the congressional township in question is basically part of this 6-mile wide strip that trends east-west, and that's called a township. And then it's also part of this 6-mile strip that trends north-south, and that's called a range. The intersection of the township and the range gives you the congressional township. That congressional township can be further subdivided into sections, and these will appear on topographic maps. And then the sections themselves can be subdivided into smaller bits that can be either quarters or quarters of quarters. So for example, this little X here occurs within a 40-acre area that would be described as the southwest one corner of the southeast one corner of section 11. And of course that section 11 is part of a congressional township, so overall it'd be southwest one corner, southeast one corner, section 11, township 1 north, because it's 1 north of the baseline, and range 4 west, because it's 4 west of the principal meridian. Here's an example showing.
Let me just say with township and range, I have never once used this in any type of my actual orienteering when I'm actually using maps. We will do it in lab because it's a thing in the lab manual, but it's not even used universally across the US. I personally don't like it, but we will be doing it, and I will walk through how to do it because it can be quite confusing.
Some of those sections, for example, here is section 4 in the middle of this topographic map of Leadville, Colorado. Let's take a look at another feature here on this topographic map. You'll notice that there are lots of little brown lines, and those lines show elevation, in other words, distance above sea level. And there are certain areas where we know exactly how far it is above sea level, like these benchmarks. So they're usually designated with a little X, and then the letters B, M for benchmark, and then the elevation itself is written in there in feet above sea level or meters above sea level. This is what a benchmark looks like if you ever find one on the ground. They're a little brass plaque that was put in that spot by whoever surveyed the elevation. And usually we use these as sort of markers to go out and figure out the exact elevation of other landscape features in that area. Now you're going to need to contour some topographic data, so let's go ahead and turn to Damon, and Damon can tell us how that's done.
So this is a topographic map, and we're going to contour the data at an increment of 5.
Okay, Damon, explain what you did here. Explain why you drew these lines where you did.
So these lines represent a difference of 5. So everything 10 and below is here. 10 to 15 would be here. 15 to 20 would be here. 20 to 25 would be here. And then the highest point, 26, would be this area down here.
So you want to imagine these contour lines as sort of every point along that line is the same distance above sea level. So
let me point out that when he was contouring that, see if I can go back here. Okay. No! Oh, shoot. Okay. So when he's contouring this, what is happening? Okay, that works. So can you see here? He has a line that's representing 10. It's slight, and our points here, we know this is 9 and that's 11, so 10 should be exactly halfway between there. So he has it too close to the 9 in this case. This line again it should go through the 10, so he's right there. Here it's 8 and 11. It should be a little bit closer to the 11 than the 8. So the 15 line should be a little bit should be closer to the 15 than it is to the 11, or the 16 than it is to the 11. So he was basically just going between the areas. He didn't actually pay enough attention that, the 20 line should be much closer to 21 than it is to 17. So he, this 30, this should be the 25 line. It should be further away from the 21. So he didn't really pay much attention to the numbers other than blocking them off and making sure he went through the exact numbers. You want to make sure that your lines are going closer to the numbers that are closer to and further away from the numbers that are further away from, if that makes sense. So I'll restart it.
These lines represent a difference of 5, so everything 10 and below is here. 10 to 15 would be here. 15 to 20 would be here. 20 to 25 would be here, and then the highest point, 26, would be this area down here.
So you want to imagine these contour lines as sort of every point along that line is the same distance above sea level. So for instance, if you had an imaginary surface that is 50 feet above sea level, the spot where that imaginary surface intersects the land is made up of a bunch of points that are all 50 feet above sea level. If you looked at it from a bird's eye view, you would see that that line basically wraps around that landscape feature, in this case an island. And the same thing for another imaginary surface at some other elevation, such as 100 feet above sea level. You can think of walking along that contour line. You would neither be going uphill nor going downhill. You're going to translate the topographic maps in lab into a topographic profile. And this is sort of like taking a samurai sword and slicing open the earth and looking at it from the side. In other words, going from the bird's eye view to going to the worm's eye view. So you're going to pick 2 points. In this case, we're going from point A to point A prime. And then we're going to lay a little piece of paper across our topographic map. Every time that piece of paper crosses the contour line, we're going to make a little tick mark on the paper and note the elevation. That can then be placed below our topographic profile, and every place where we know the elevation, we go ahead and we put a little dot and then connect those dots. So for instance, here's the profile that's provided in your lab manual. You would go ahead and note the position of the elevation at various points along that profile. Then you would connect those dots to show what the land looks like from the side, and then mentally you could fill in everything below that line.
I want to point out before this page goes away, note the selection of vertical scale has caused exaggeration in the slope of landforms. So this means that 1 foot vertically is not 1 foot horizontally. So that means that these are emphasized. This is actually fairly typical. They normally will tell you that it's something like 5 times vertical exaggeration. So typically you will see that your lab book, I believe, gives you the vertical elevation, so it will have exaggeration. I just want to point out that's what this means here.
As land and everything above it as empty air. So if you were to look at this landscape from the side, people would be standing on the land surface, something like that. Although you note from the scale, that would be a very tall person indeed. All right, good luck with lab this week. I hope you enjoy viewing the Earth's surface from these 3 different perspectives.
All right, and that is it for the pre-lab video, and that is it for this lecture. So see you next time.